Hello all. In my previous lecture, I discussed semiconductor material, that is our chapter 2, that is classification of the semiconductor material, that is intrinsic semiconductor and extrinsic semiconductor, right? And also we discussed intrinsic semiconductor and their electrical characteristics like current density and conductivity, resistivity. Okay. And one more topic actually calculation of the intrinsic concentration. Okay. And calculation of Fermi level in an intrinsic semiconductor. Right. Now I start with the problem. Calculation of intrinsic Fermi level. That is problem question number 2 in our classroom workbook. Yeah. First I done a question. A pure germanium sample has Mn equal to 0.5 MP. Mn equal to 0.5 MP at room temperature. Find position of the Fermi level. With respect to middle of the Fermi band. Right. First, what is the given data actually? They given a pure germanium sample and it has Mn equal to 0.5 MP at room temperature, right? What we want to calculate actually position of the Fermi level, right? See, in case of intrinsic semiconductor, what is the intrinsic Fermi level actually? EFI equal to EC plus EV by 2 minus KC by 2 ln of Mn by MP whole power 3 by 2, right? This is the Fermi level equation in case of intrinsic semiconductor. What we want to calculate actually here, Fermi level with respect to middle of the Fermi band. What is the middle of the Fermi band actually? See here, energy band diagram. This is the conduction band and this is the valency band. This is EC, this is EV. Middle means EC plus EV by 2, right? Middle of the Fermi band is nothing but EFI minus EC plus EV by 2, which is equal to KT by 2 ln of Mn by MP whole power 3 by 2. What is KT here? KT is nothing but 0.026 by 2 ln of Mn. Mn is nothing but 0.5 MP whole power 3 by 2. So this value is equal to 0.027 electron volt, right? Here question is not completed actually. Here what we want to calculate position of the Fermi level, right? Where is the position actually, right? Here this EFI minus EC plus EV by 2 is positive or negative? Positive, right? It is positive means where is the Fermi level actually? It lies above the middle of the Fermi band. This is the position actually. Yeah, above the middle of the Fermi band. Yeah, copy. Next topic, extrinsic semiconductor, classification of the extrinsic semiconductor, that is n-type semiconductor. Yeah. Copy the heading first. Right. See here, we have two types of extrinsic semiconductors actually, depending upon adding of impurity atoms, okay, that is n-type semiconductor and p-type semiconductor. Here, first of all, how this n-type semiconductor is formed? This n-type semiconductor is formed by adding pentavalent impurities to the pure form of semiconductor like silicon or germanium. What are the pentavalent impurities actually? The pentavalent impurities are nothing but nitrogen, phosphorus, arsenic, antimony, bismuth. Right? Here, the nitrogen cannot be used. Nitrogen cannot be used because it does not have any tendency to donate an electron. That's why nitrogen cannot be preferred for making of n-type semiconductor. And one more, bismuth also cannot be preferred for making of n-type semiconductor because it is a radioactive element. Okay, that means which elements are preferred actually? Phosphorus, arsenic, antimony, depends on your requirement of an application. Depends on your electronic device. Okay, yeah, note, write down the notes. Write down the notes. These are formed by adding pentavalent impurities, to the pure form of semiconductor, like silicon or germanium. Example, nitrogen, write down like this: nitrogen, phosphorus, arsenic, antimony, bismuth. Next, nitrogen cannot be used. Next point, nitrogen cannot be used because it does not have any tendency to donate an electron. Next point, bismuth also cannot be preferred. Because it is a radioactive element. Right. Next, copy this diagram. Parallelly. right? So now, see, this entire semiconductor is formed actually by adding the pentavalent impurity to the pure form of semiconductor. You know, this added pentavalent impurity can replace the semiconductor atom, due to which the 4 valence electrons are involving in covalent bond formation, and the 5th valence electron does not involve any covalent bond formation, due to which the free electron concentration is increases, and also the recombination rate is also increases. Recombination rate also increases. That means the few free electrons are recombined with the holes present in the intrinsic semiconductor. As a result, the hole concentration is decreases. Okay, that means in case of n-type semiconductor, the majority charge carriers are free electrons and the minority charge carriers are holes, right? See, for better understanding actually here, I would like to explain like this. See, pure semiconductor means what will be the condition actually? N equal to P, right? Here we are adding which type of impurities? Pentavalent impurities, right? In pentavalent impurities, actually the 4 valence electrons are involving in covalent bond formation. What about the 5th one actually? Does not involving any covalent bond formation. This is the 5th one. This is the 5th one. Due to this, the free electron concentration is increases. Okay, and also when we add this pentavalent impurity to the pure form of semiconductor, what happen? These few free electrons are recombined with the holes present in a intrinsic semiconductor. Okay, due to which the hole concentration is decreases. See here, one side the electron concentration is increased because of adding of impurities. Other hand, the hole concentration is decreased because of recombination. That means simply we can say the majority charge carriers are electrons and the minority charge carriers are holes. And also one more point actually, this added pentavalent impurity can donate this 5th valence electron to the nearby atom, so that it is also called as donor impurity. What it called? Donor impurity. That is ND. Right? Write down. Write in the notes. The added pentavalent impurity can replace the semiconductor atom, due to which 4 valence electrons are involving in covalent bond formation. 4 valence electrons are involving in covalent bond formation, and 5th valence electron does not involve any covalent bond formation. Due to which free electron concentration is increases. Right? Recombination rate is increases. That is, few free electrons recombine with holes. As a result, hole concentration is decreases. Yeah. Now underline, free electron concentration increases, recombination rate is increases, hole concentration is decreases. Hence, next point. Hence, the majority charge carriers are free electrons and minority charge carriers are holes. Next point. The added pentavalent impurity can donate 5th valence electron to the nearby atom. So that it is also called as donor impurity. It is also called as donor impurity. Underline donor impurity. Underline donor impurity. Right. Yes. Next topic. Charge neutrality or electrical neutrality of a n-type semiconductor. Yeah. Next. Charge neutrality or electrical neutrality of a n-type semiconductor. Put the heading. Yeah. See, what is charge neutrality or electrical neutrality actually? Anybody? Right. See, for example, this class cannot maintain the charge neutrality. What is the meaning? You know, the net amount of negative charge is not equal to net amount of positive charge. Then what we can understand what is mean by charge neutrality? Charge neutrality is nothing but the net amount of negative charge equal to the net amount of positive charge. Right? Here, entire semiconductor is said to be electrically neutral or charge neutral because net amount of negative charge is equal to net amount of positive charge. Not only in entire semiconductor, in case of any material, okay, it must satisfy the charge neutrality. That means the net amount of negative charge equal to the net amount of positive charge. Yeah. Here, what is the net amount of negative charge in entire semiconductor? And what about the net amount of positive charge in entire semiconductor? See here. See, the net amount of negative charge in entire semiconductor is nothing but free electron concentration, Nn. That is denoted with Nn. Nothing but free electron concentration in entire semiconductor. What about the net amount of positive charge actually? Pn. Whole concentration in entire semiconductor, right? Now this is what actually N equal to P. N equal to P means this is for intrinsic semiconductor. But here entire semiconductor means it's an extrinsic, right? Now we can add one more actually. Okay, when we add the pentavalent impurity to the pure form of semiconductor, what happens? Which concentration will be decreased? Whole concentration will be decreased, right? That means we can add the donor concentration on P side to balance this equation, right? Now, what is this equation actually? Charge neutrality or electrical neutrality equation of a n-type semiconductor. Right? N equal to P means that is the charge neutrality equation for intrinsic semiconductor. N equal to P plus Nd is nothing but this is the charge neutrality equation for what? N-type semiconductor. Right. Right out. Add in the notes. Any material is said to be electrically neutral or charge neutral, because net amount of negative charge equal to net amount of negative charge is equal to net amount of positive charge. Right? Next point. N-type semiconductor is said to be electrically neutral or charge neutral, because, yeah, write on this one, net amount of negative charge equal to net amount of positive charge, and copy this equation. Right. Right on. Where Nn is the free electron concentration in entire semiconductor. Free electron concentration in entire semiconductor. Next, Pn is the whole concentration in entire semiconductor. Whole concentration in entire semiconductor. Next, Nd is the donor concentration. Nd is the donor concentration. Right. Next, so now here how to calculate this free electron concentration and the whole concentration in entire semiconductor by using mass action law. By using mass action law, right? What is mass action law actually? This mass action law is nothing but the product of electron concentration and the whole concentration is equal to square of intrinsic concentration. Square of intrinsic concentration, that may be intrinsic semiconductor or extrinsic semiconductor, right? From this we can calculate this free electron concentration and whole concentration, right? For calculation of this free electron concentration and whole concentration, consider this one as equation 1. Now you can consider this one as equation 2, right? Now substitute equation 2 in equation 1. Nn equal to Pn is nothing but Ni square by Nn plus Nd. Now Nn square minus Nd into Nn minus Ni square equal to 0. Right? See here, this is clearly a quadratic equation, right? How to solve this one actually? I think you know minus b plus or minus root of b square minus 4ac by 2, right? So here, then what is Nn value here? Nn equal to minus b. Minus b is nothing but Nd plus or minus under root b square. B square is nothing but minus Nd square, right? That is simply Nd square minus 4ac, right? A is nothing but 1 and C is nothing but minus Ni square. This becomes plus Ni square by 2a, right? This is 1. Now here, but concentration must be in positives. But concentration must be in positive value, right? So that neglect negative value, right? Then what will be the electron concentration? Nn equal to Nd plus Nd square plus 4 Ni square by 2. And how to calculate whole concentration actually? Ni square by Nn. Right. So with help of these two formulas actually we can calculate free electron concentration and whole concentration, right? Now this is an exact formula. Right? I can also go for approximation actually. What is an approximation? If Nd is far greater than Ni. If Nd is far greater than Ni, then what is the electron concentration actually? Electron concentration is approximately equal to Nd plus Nd square by 2, right? Now what is this actually? Nn is approximately equal to Nd, and what about the Pn actually? The Pn is approximately equal to Ni square by Nd. Yeah, these two formulas are called as what actually? Approximate formulas, right? Copy. These are the free electron and whole concentrations. Copy. Calculation of conductivity of a n-type semiconductor. Of a n-type semiconductor, that is sigma n. Yeah. So how to calculate the conductivity of n-type semiconductor? First, I can define for any semiconductor. For any semiconductor means that may be intrinsic or extrinsic. What should be the conductivity actually? N into E into mu n plus P into E into mu p. Right? Now I can define for n-type semiconductor. For n-type semiconductor, what should be the conductivity? Actually, sigma n equal to Nn into E into mu n plus Pn into E into mu p. Right? This is the conductivity equation for n-type semiconductor, and this formula is the exact formula. Now I can also go for approximation actually. In case of n-type semiconductor, which one is the majority electrons and which one is the minority holes? That means we can consider like this. So the free electron concentration is clearly far greater than hole concentration. Then what should be the conductivity equation? Actually, sigma n is approximately equal to Nn into E into mu n. But in approximation, what should be the free electron concentration? Nd. That is Nd into E into mu n. Right. This is the conductivity equation of n-type semiconductor. Copy? Right. Write in a question. In classroom workbook, the question number 3. Question number 3. Write in a question. A pure silicon sample is doped with. A pure silicon sample is doped with phosphorus. Is doped with phosphorus to the extent of 1 out of 10 power 6. To the extent of 1 out of 10 power 6. If Ni equal to 1.5 into 10 power 10, 1.5 into 10 power 10 per centimeter cube, comma, atomic density of silicon is 5 into 10 power 22, 5 into 10 power 22 per centimeter cube. Mu n equal to 1300 centimeter square per V second. Centimeter square per V second. Calculate the first bit, carrier concentrations. The first bit, carrier concentrations. Second bit, conductivity. The first bit, carrier concentrations. Second bit, conductivity. Here, what is the given data actually? So they given a pure silicon sample, right? It is doped with phosphorus. Then what is the sample become N type? Yeah, how it will doped actually? 1 out of 10 power 6. What is the meaning actually? You know, for 10 power 6 silicon atoms actually, okay, how many impurities are added? one impurity is added, means one phosphorus atom is added. One phosphorus atom is added. The given atomic density of silicon, how much actually? 5 into 10 power 22, right? See, 5 into, see, for 10 power 6, one impurity is added here. For 5 into 10 power 22 silicon atoms here, how many impurities are required actually? Simply 5 into 10 power 22 by 10 power 6. So, which is equal to 5 into 10 power 16. So, this much of impurity is added to the N-type sample, right? You know what is this? This is simply a ND, donor concentration. This is simply an ND. Also, they given a intrinsic concentration, that is Ni equal to how much? 1.5 into 10 power 10. Also, they given a mu n equal to 1300, right? Here, what is the first bit actually here? Carrier concentration. See, for calculation of carrier concentration, we have two formulas. One is exact formula, another one is approximate formula, right? See, for this example, the which one is suitable actually, exact or approximate? Approximate, right? How you know whether we can choose exact or approximate actually? See these two concentrations. Here Nd is how much? 5 into 10 power 16. Ni is 1.5 into 10 power 10. I think clearly this is 10 power 16, this is 10 power 10, right? So clearly Nd is far greater than Ni. Yes or no? 10 power 16, 10 power 10. Then we can go for approximation, that is Nn is approximately equal to Nd, but Nd is 5 into 10 power 16, right? And what about the Pn actually? The Pn equal to Ni square by Nd. What is Ni here? 1.5 into 10 power 10 whole square by 2 by Nd. Nd is nothing but 5 into 10 power 16. So which is equal to 4500 per centimeter cube. So these are the carrier concentration in a N-type sample. Also we want to calculate the conductivity of this sample, right? What is the conductivity equation actually? So conductivity is nothing but approximately equal to Nd into E into mu n. What is Nd here actually? Nd is nothing but, so 5 into 10 power 16, charge of electron 1.6 into 10 power minus 19, mu n is nothing but 1300. Then what is this value actually? 10.4 ohm centimeter whole power inverse. This is the conductivity of sample, right? Copy. Yeah. Next topic. Calculation of Fermi level of a N-type semiconductor, in bracket, that is EFN, right? See how to calculate the Fermi level of a N-type semiconductor actually. Right. First I can define for any semiconductor. For any semiconductor, what is the equation of electron concentration? N equal to Nc into E power minus of Ec minus Ef by KT. Yeah, consider this one as equation 1. Similarly, for N-type semiconductor, for N-type semiconductor, what should be the electron concentration? N equal to Nd and EF equal to EFN. This is equation 2, right? See, from equation 1 and equation 2. Now, what is this actually? Nd is approximately equal to Nc into e power minus of Ec minus this EF becomes EFN by kT, right? Now, Nc by Nd is approximately equal to e power Ec minus EFN by kT. Take logarithmic on both sides, then Ec minus EFN by kT equal to ln of Nc by Nd. Now, Ec minus EFN is equal to kT into ln of Nc by Nd. Now, what about the EFN actually here? EFN is equal to Ec minus kT into ln of Nc by Nd. Now, see this equation actually. Now, see this equation. What is the conclusion here? For an n-type semiconductor, where is the Fermi level actually from this equation? This is the conduction band, this is EV and this is EV, this is EC. See, EFN equal to EC minus KT into ln of NC by Nd. I think this value is very, very small, right? EC minus. EC minus means, I think, for an n-type semiconductor, where is the Fermi level actually? The Fermi level is nearer to the conduction band. This is the position of the Fermi level in case of n-type, right? Copy. Right. Write down. That is for an n-type semiconductor, the Fermi level nearer to the conduction band. The Fermi level lies nearer to the conduction band. Right. Next heading, note. Very, very important note actually. Note. See, if Nc is greater than Nd, means what is Nc actually? Density of energy states in conduction band, which is greater than donor concentration. What about the EFN minus EC actually? EFN minus EC is negative, right? If Nc is greater than Nd, this EFN minus EC is negative. Then where is the Fermi level actually? The Fermi level is lies below the conduction band, right? Similarly, if Nc is less than Nd, then what about the EFN minus EC actually? Positive. EFN minus EC is positive means where is the Fermi level actually? The Fermi level is lies within a conduction band. The Fermi level lies within a conduction band. Next one, if Nc equal to Nd, then what about the EFN minus EC actually? The EFN minus EC equal to 0. EFN minus EC is 0 means actually, where is the Fermi level actually? The Fermi level is coincide with the conduction band, right? That means what is the conclusion actually? The conclusion is the Fermi level lies within a conduction band or coincide with the conduction band, such a semiconductor is called as a degenerative semiconductor, n-type semiconductor or heavily doped n-type semiconductor. Right? Similarly, if the Fermi level lies below the conduction band, such a semiconductor is called as what actually? Non-degenerative semiconductor or a lightly doped semiconductor. Non-degenerative semiconductor or lightly doped semiconductor. Right? See here, why it is called as degenerative, why it is called as non-degenerative, you know, when the doping concentration is increases, right, the generation will be decreases. That's why it is named as degenerative. Right? When the doping concentration is decreases, then what happens actually? The generation is increases. So here, that's why it is named as non-degenerative. Right? Now, what is the conclusion actually here? What we can observe, if the doping concentration is increases in n-type sample actually, what will be the Fermi level? The Fermi level is moving towards conduction. That is the final one. Right? Write down. Write down your notes. Write down. Case 1. If NC is greater than ND, if NC is greater than ND, then EFN minus EC equal to negative. EFN minus EC equal to negative. That is, the Fermi level lies below the conduction band. The Fermi level lies below the conduction band. Right. Next, case 2. If NC is less than ND, if NC is less than ND, then EFN minus EC equal to positive. EFN minus EC equal to positive. That is, the Fermi level lies within a conduction band. The Fermi level lies within a conduction band. Next, case 3. If NC equal to ND, then EFN minus EC equal to 0. EFN minus EC equal to 0. That is, the Fermi level coincide with the conduction band. The Fermi level coincide with the conduction band. Right. Next heading, conclusion. Next heading, conclusion. Conclusion. Right. The n-type semiconductor in which the Fermi level lies within a conduction band, or coincide with the conduction band, such a semiconductor is called as degenerative n-type semiconductor or heavily doped n-type semiconductor. Heavily doped n-type semiconductor. Yeah. Next, underline degenerative or heavily doped n-type semiconductor. Next point. The Fermi level lies below the conduction band. The Fermi level lies below the conduction band. Such a semiconductor is called as non-degenerative n-type semiconductor or lightly doped n-type semiconductor. Yeah, underline non-degenerative or lightly doped n-type semiconductor. Right. Yeah. Next, conclusion. Completed, right? Next, observation. Write down. In n-type semiconductor, doping concentration is increases doping concentration is increases, then the Fermi level move, the Fermi level move, the Fermi level move towards the middle, the Fermi level move towards the conduction band, towards the conduction band, yeah. Underline the statement that in enter semiconductor sample, doping concentration is increases, the Fermi level move towards the conduction band. Completed? Right. Thank you. Yeah. To be continued in next lecture.